In this video, we're going to look at non-homogeneous linear equations. We're going to explore two methods for finding a particular solution x sub p of non-homogeneous equations. The first method we're going to explore is a method of undetermined coefficients. Given a linear constant coefficient of an ordinary differential equation of any order n, in the form of a sub n x raised to the n, a sub n minus 1 x raised to the n minus 1 plus ... all the way down to a sub naught x is equal to some function in terms of t being the independent variable. The general solution will be x is equal to x sub h, which is a homogeneous, plus x sub p, which is a particular solution. We will look at the method of undetermined coefficients to find x sub p. This method only works when the coefficients are constants and the function f of t is exponential. Linear combinations of sines and cosines, a polynomial, or possibly in algebraic combinations of such functions. I call this the guess and check method. The best guesses to start with are, if we have a function that is an exponential is of the form a e raised to the bt, where I have capital A e raised to the bt, and an example of this would be 5 e raised to the negative 2t, and this is my f of t. Then an appropriate use for x of the particular would be a e raised to the negative 2t. If I have a polynomial of degree n, so as an example, I would have 1 plus 2t minus 7t raised to the third power. Then an appropriate choice to guess and start with would be a plus bt plus c t squared plus d cubed. And that's because this is a polynomial of degree 3. So then I would need a polynomial of degree 3 to use as my particular solution. If I have some form of sine of alpha and cosine, so a sine bt plus b cosine bt, that's a beta, excuse me. And as an example, I have negative 2 cosine 5t, then an appropriate choice to guess and check with would be a cosine 5t plus b sine of 5t. Now, something to note, we can't assume that the solutions to non-homogeneous equations are always going to trend towards zero, even if the homogeneous solution is a sum of negative exponential functions. So first we're going to start out with finding the general solution to x double prime of t, 5 prime of t, for x of t is equal to 0. Now this is homogeneous, so we know with a homogeneous function we would start out with finding the characteristic polynomial. So this would be r squared plus 5r plus 4 is equal to 0. This, of course, factors into r plus 4, r plus 1, which gives us x sub t is equal to c sub 1 e raised to the negative t plus c sub 2 e raised to the negative 4t, because as you recall from our previous video, that these roots become the powers of the exponents where I've got the b. That becomes the b up here of this form a e raised to the bt. Now this is as good as it gets unless we had an initial value. And then of course we could solve for c sub 1, c sub 2. But this is a family of functions that satisfies this ODE. If I wanted a particular family member, I would need to have an initial value. So let's take a look at this example. We want to find the general solution to x double prime of t plus 5x prime of t plus 4x of t e raised to the negative 2t. Now we know from the previous example that the homogeneous system is going to be of this form. X sub homogeneous of t would be c sub 1 e raised to the negative t plus c sub 2 e raised to the negative 4t. Now we know that this is non-homogeneous, and this is our f of t. So a good guess for the particular solution, p of t, would be ae raised to the negative 2t. Then x prime of t, x prime sub p of t is equal to negative 2 a e raised to the negative 2t. And then the second derivative, x double prime sub p of t, would give me 4ae raised to the negative 2t. Then my x sub p double prime of t plus 5x prime of p of t plus 4x p of t is going to be e raised to the negative 2t. That tells me, replacing this x double prime sub p of t with this 4, I would have 4ae raised to the negative 2t. Replacing this with the negative 2ae raised to the negative 2t would be plus 5 multiplied by negative 2ae raised to the negative 2t plus 4, and then again, this is my x sub p, so I'd have 4ae raised to the negative 2t would be equal to e raised to the negative 2t. Now on the left-hand side, I'm going to combine up all of these terms, and so I have 4 minus 10 plus 4 gives me a negative 2ae raised to the negative 2t, which is equal to e raised to the negative 2t. And that means that a must be equal to negative 1/2. Therefore, my particular solution would then be negative 1/2 e raised to the negative 2t. That means my final solution, my x of t, which is the combination of my homogeneous and my particular, will be equal to c sub 1 e raised to the negative t plus c sub 2 e raised to the negative 4t minus 1/2 e raised to the negative 2t. So basically what we do when we want to find the solution to a non-homogeneous linear with constant coefficients is we start out with what the homogeneous solution would be, and that would be setting this thing equal to 0, find the characteristic polynomial that's associated with this ODE. And then based on f of t, we will then make a good guess as to what the particular solution would be. We then do a couple of derivatives or whatever it is required here to match up. And then, of course, coefficients must match. So we know that negative 2 multiplied by a, in this case, has to equal 1. That means a has to equal negative 1/2. Now let's take a look at this one. Now, when we take a look at this one, we know the homogeneous solution, of course, is the same because I'm using the same characteristic polynomial for all of these. So I can really just focus in on the particular solution. So we know this is c sub 1 e raised to the negative t plus c sub 2 e raised to the negative 4t. Now in this case, our f of t is e raised to the negative 2t, which we see is right here. Now we know from our last video, when this happens, when we have these, quote, repeated roots or repeated values, then of course our, that should be homogeneous up here. Let me subscript this h, by the way. Then a good choice for our particular solution would be a t e raised to the negative t. Now this eliminates the fact that we would have normally have had the exact same solution potentially because of being repeated roots. So that's why I added this t, is because this f of t potentially matches one of the homogeneous solutions. So it would be almost like a repeated root. Now, what I'm going to do then is I'm going to do my second derivative and my first derivative, just like I did before. So I have x prime sub p of t. Now what I have to do here is, of course, take care of the fact that we have a product rule here. So this is going to be a and then e raised to the negative t minus t e raised to the negative t. And then my second derivative of the particular solution, my guess, would be a negative e raised to the t, negative t, minus e raised to the negative t, plus t e raised to the negative t. Now, as before, I'm going to go back to my original ODE, And I'm going to put my second derivative as a replacement for this x double prime, my first derivative as its replacement for x prime, and of course I have 4 times what my guess is. So, and I set it equal to my f of t. So I'm going to start out with my x double prime, and that is going to be the a negative e raised to the negative t minus e raised to the negative t plus t e raised to the negative t. That is this replacement right here. Plus 5a, I'm going to replace x prime of t, and I have e raised to the negative t minus te raised to the negative t. And I'm going to replace this with my original good guess, so plus 4a te raised to the negative t, and I set this equal to e raised to the negative t. Now after my algebraic cleanup, this entire side, I'll go all the way down here. When I do my algebraic cleanup, this becomes 3ae raised to the negative t, which is equal to e raised to the negative t. That tells me my a is 1/3. So my solution x of t, which of course is the homogeneous plus my particular, is going to be, again, it is c sub 1 e raised to the negative t plus c sub 2 e raised to the negative 4t plus 1/3 e raised, and I should have a t there, my apologies. Let me go ahead and put that t right there. So 1/3 t e raised to the negative t. Okay, let's take a look at another example in which I'm going to have 2 more examples. One is where I've got the sine and cosine, and one is where I have a polynomial. So we already know what the particular solution is, or the homogeneous solution, so I'm not going to take the time. And so what I'm going to do instead is say, I think this is a good choice for my particular solution. A cosine of t plus b sine of t. And that's because the multiplier on that t is 1. Therefore, the multiplier on these t's would also be 1. So I just wanted to point that out, why I have just t there. And again, I would go through my first and second derivatives, x double prime, or x prime of t, x double prime of t. I would then put that back into my original equation, and this is what I end up with. And I'm not going to go through all those because it's kind of boring. So what I end up with is I end up with 2 the cosine of t, because that's my f of t. And it will be equal to 3a plus 5b the cosine of t plus negative 5a plus 3b the sine of t. Now, that tells me that my equations are 3a plus 5b must be the coefficient on cosine, which is 2, and negative 5a plus 3b must be the cosine on sine, which is 0. And so then I get a is equal to 3/17 and b is equal to 5/17. So again, my final solution x of t, which is going to be equal to the homogeneous c sub 1 e raised to the negative t plus c sub 2 e raised to the negative 4t, and then plus this particular solution, which is 3/17 the cosine of t plus 5/17 the sine of t. Now let's look at when we have a polynomial. Now, a good choice, because as a polynomial of degree 2, would be x of p of t would be equal to a plus b of t plus c of t squared. This is because it's a polynomial of degree 2. I would find my first and second derivatives, and then I would set them equal, and what I get is I have 2c plus 5b plus 2ct plus 4a plus bt plus ct squared is equal to this polynomial, which is 1 plus 2t minus 4t squared. And so what I'll end up with, multiplying everything out and putting coefficient to coefficient power with the same powers. If I look at my constants first, my constants would be 2c plus 5b plus 4a is equal to 1. Looking at my t term, I would have 10c plus 4b is equal to 2. And then looking at my t squared, I'm going to have c, 4c, is equal to negative 4. So then doing however you like to solve, whether it is using matrices or just back substitution or however you want to do, I end up with a is equal to negative 3, b is equal to 3, and c is equal to negative 1. So my x sub t, which is equal to my homogeneous c sub 1 e raised to the negative t, plus c sub 2 e raised to the negative 4t, plus I'm going to have negative 3 because that is my a. And then I'm going to have, because I remember a was the constant, and then I'm going to have plus 3 times t because b was the coefficient on my t, and then minus t squared because negative 1 was the coefficient on the t squared term. And that is my final solution. We end up with this lemma that says, if x sub a is a solution of x double prime of t, p of t, x prime of t, q of t, x of t, and f of t, and x sub b is a solution of the x double prime of t, p of t, x prime of t, q of t, x of t is equal to g of t, then the sum of x sub a, x sub b, which is equal to x, is a solution of x double prime of t, p of t, x prime of t, q of t, x of t, f of t, plus g of t. You're like, what just happened? Now notice that this entire ODE is this entire ODE. So if this entire ODE is equal to f of t, and x sub b is a solution of this, or x sub a is a solution of this, and again, this entire ODE matches this ODE, and x sub b is a solution of this with this particular g of t, then the sum of these two have to be a solution of this entire ODE plus the sum of those two f of t and g of t. And you're like, why are you telling me this? Well, this is what happens when we have a mix of solutions, right? Now, my f of t here is not just e raised to the negative 2t. That's my exponential. But I have a g of t here, which is to the cosine of t. Now, we use the fact that if x sub a is the solution, where I've got f of t maybe be the exponential, and g of t is maybe this trig function, then using this lemma, we can find this solution. Now, we know from our previous example that my x sub p of this one, which I'm going to call x sub a of t, we know from our previous example that this particular solution was a negative 1/2 e raised to the negative 2t. Now, we're going to call this x sub b, and we know from our previous example of t, let me shove that in there, was 3/17 the cosine of t plus 5/17 the sine of t. So my final solution, x of t, is equal to my homogeneous, which is still the same because I'm using the same ODE, just to show you that I'm not really focusing on that. It's not as important once you have the homogeneous how to find the rest of them. So c sub 1 e raised to the negative t plus c sub 2 e raised to the negative 4t minus 1/2 e raised to the negative 2t plus 3/17 the cosine of t plus 5/17 the sine of t. Okay, so now let's just recap what I've done. Is that basically if I have something that looks like this, the first thing I'm going to do is find my homogeneous. Now, even though it's not homogeneous, I start out with my homogeneous solution for linear differential equations with constant coefficients. Then what I do is I realize that this is an exponential and this is a trig function, so I am going to individually solve this using first a good guess for the exponential and then a good guess for the trig function. And that's how you approach that. All right, so this is how you approach it, and you end up with this. So you end up probably thinking, if you want to think about this, you end up doing 3 different equations. One where it's just a homogeneous, one where it's a good guess for the exponential, and one which is a good guess for this one. So that's how you just kind of have a recap of everything we've done. Now, I just want to take a look at B here. B is different in the fact that I now have a polynomial that isn't like the same ones. So I have, however, a TE raised to the 4t. Now, I'm not going to bore you with the homogeneous, but I can tell you what the homogeneous is. X of homogeneous of t is equal to C sub 1 e raised to the 6t plus C sub 2 e raised to the negative 2t. So now, how do we address this e raised to the 4t? Well, this kind of looks like a polynomial multiplied by an exponential. So a good guess for the polynomial, which is the t part, would be a plus b of t. That's a good guess for the polynomial part. Now, a good guess for the exponential part would be CE raised to the 4t. Now, this is a good guess, and that's because we have a polynomial multiplied by an exponential. So this is the good guess for my polynomial of degree 1, and here's a good guess for my exponential. Now, herein lies a slight little problem. I've got 1, 2, 3 unknowns. When I put that into here, like I have in the past, I'm going to end up with only 2 equations, but I have 3 unknowns. But we can fix this. The way that we fix this is, let's multiply that constant through. So I'm just going to rewrite this as e raised to the 4t. I'm going to multiply the constant through, so I have c times a plus c times b t. Now you're thinking, how did that help me? Well, here's the thing. CA, which is a constant times a constant, is just a constant. CB, which is a constant times a constant, is just a constant. So I'm just going to relabel this e raised to the 4t a plus bt. And that's because this is just a constant, this is just a constant. So I'm just going to relabel the constant multiplication as the constant a and the constant b. We can do that because it's just a constant. It's just like when we're in calculus and we do the integration. Notice how when we do integration by parts and we multiply that 3 through, or whatever we do when we do the integration, we have to do something with that constant. We just say, oh, it's still just a constant because it's a multiplication. Now, so then my good guess, my x sub p of t, my good guess would be e raised to the 4t a plus bt. Now this is exactly like we expect. We do our first and second derivatives, and we put our first and second derivatives back into this equation here for each one of those y of t. Oh, they should all be y of t. I guess we're using y of t this time, so let me change this to y of t. And we do our usual stuff, and what I end up with is I end up with negative 12a e negative 12at e raised to the 4t plus 4a minus 12b e raised to the 4t, which is equal to te raised to the 4t. And like we do before, we're going to set the term, which is the te raised to the 4t. We're going to start with that one, and we have negative 12a is equal to 1, and then my e raised to the 4t term, I'm going to have 4a minus 12b is equal to 0. So I end up with A is equal to negative 1/12 and B is equal to negative 1/36. So what I end up with then for my particular solution, my y of particular of t, is going to end up being e raised to the 4t. My A is negative 1/12 minus my B, which is 1/36, multiplied by t. Then what I end up with as my final, and it should be y, I don't know why I'm doing x sub t, which was my homogeneous from up above, c e raised to the 6t, plus c sub 1, c sub 2 e raised to the negative 2t, plus e raised to the 4t, negative 1/12 minus 1/36 t. And that is my general solution. There are a couple of rules that you need to remember for products. If f of t contains an exponential, ignore it and write down the guess for the remainder. Then tack on the exponential without any leading coefficient. This is kind of important. That was what I just did to show you that I would have, in my previous example, I would have had 3 unknowns but only 2 equations. For the product of polynomials and trig functions, you first write down the guess for just the polynomial and multiply that by the appropriate cosine. Then add a new guess for the polynomial with a different coefficient and multiply it by the appropriate sign. The last thing we're going to learn is variation of parameter. Now, what we just learned in our previous examples works for a very small set of ODEs. And sometimes the algebra can get a little messy. So now we're going to learn the method of the variation of parameters. It's a general method, and it can be used in most cases. Well, actually, more cases, I should say, not most cases, but more cases than what we just did. The one that we just did is such a small percentage of ODEs. However, there's a couple of disadvantages to this method. First, the homogeneous system solution is required to do it in this method. This is a contrast to the method of undetermined coefficients, where it was advisable to have the homogeneous solution on hand, but wasn't required. So all the ones I did before, I didn't necessarily need the homogeneous solution, but it is highly recommended. In fact, in the one I had to have it so that I didn't get led astray. This method, variation of parameters method, you absolutely need to have the homogeneous solution. And sometimes you'll see when you pick up your ODE book, it's called a complementary solution because it's not truly a homogeneous ODE. So I just want to say that. So we'll need to always start out with that. The other thing about the variation of parameters is we're going to need to do a couple of integrals. And there's no guarantee that we'll be able to do these integrals. So while it's always possible to write down a formula to get a particular solution, we may not actually be able to find it if the integrals are too difficult or if we're unable to find the homogeneous or complementary solution. So I just wanted to just give you that bit of information before we dive in. So here we go, variation of parameter. Suppose we have this ODE and a solution to the associated homogeneous equation, also known as a complementary solution, is of the form c sub 1 x sub 1 and c sub 2 x sub 2. Now x sub 1 and x sub 2 could be exponentials, it could be polynomials, we don't know. These x sub 1, x sub 2 does not necessarily mean that they're just x's. I just want to say that out of the gate. Then the particular solution x sub p is assumed to be a linear combination of these two x sub 1, x sub 2, and in the form of the particular solution is v1 of t x sub 1 and v2 x of t x sub 2, where v1 of t and v2 of t are non-constant functions. Then its derivative would look like this, using the product rule. In order to simplify x prime of p and x double prime of p, the first condition we must impose is this: x prime sub 1 of t x sub 1 plus v prime sub 2 of t x sub 2 is equal to 0. Then x prime of p will give us v sub 1 t x prime 1 x prime sub 1 plus v sub 2 t x prime sub 2, which leads us to our second derivative. So my second derivative plus my p of t times my first derivative, q of t, f of t becomes this thing. Now, when we group together and we say this is equivalent to 0 and this is equivalent to 0, then we end up with this. Now, the second condition we have to impose is v sub 1 of prime of t x prime sub 1 plus v prime sub 2 of t x prime sub 2 is equal to f of t. So now we have these two equations for the v sub 1 prime of t and v sub 2 prime of t is equal to this. Using Cramer's rule, good old Cramer's from linear algebra, we end up with v sub 1 prime is equal to this. V sub 2 prime is equal to this. Which, if we notice that the denominators of both of these are the Wronskian, and finally, this is what we get. V sub 1 is equal to the negative integration of x sub 2 of f with a Wronskian x1, x2 of dt, and v sub 2 is equal to the integration of x sub 1 f, the Wronskian dt. Now I just want you to note that if I'm looking for v sub 1, notice how I use x sub 2 here. If I'm looking for v sub 2, notice I use x sub 1 here. This is a negative, this one is a positive. But other than that, it's pretty much the same formula. So let's find the general solution using the variation of parameters. Now, homogeneous solution, first thing we're going to do before we find the homogeneous or complementary solutions, divide everything by 2. And we end up with y double prime of t plus 9y of t is equal to 3, the tangent of 3t. I'm not going to go through how to find the homogeneous or complementary solution because we've done this a couple of times, so I'm just going to tell you what it is. Y of the homogeneous part is equal to c sub 1 cosine of 3t and plus c sub 2 the sine of 3t. So my y sub 1 of t would be equal to the cosine of 3t. My y sub 2 of t would be the sine of 3t. So first I have to find that. Now my Wronskian then would be my cosine of 3t and its derivative, which would be negative 3, the sine of 3t, my sine of 3t and its derivative, which would be 3, the cosine of 3t. And then this would end up giving me 3, the cosine squared of 3t, plus 3, the sine squared of 3t. Now, we know that if we factor it out of 3, we end up with an equivalent of 1, because cosine of an angle plus sine of the same angle is equal to 1. So this just gives me 3. Now, for the particular solutions then, we're going to have y of my particular solutions would be equal to negative, using this formula up here. So we have negative the cosine of 3t integrated by 3, the sine of 3t, the tangent of 3t, divided by the 3, because that's my Wronskian value, dt, plus the sine of 3t multiplied by the integration of 3, the cosine of 3t, the tangent of 3t, all divided by my Wronskian, which was a nice 3 dt. Now, I'm not going to go through the integration for you, so I'm just going to jump right to my final answer for this, this is then going to be negative cosine 3t divided by 3, and I have the natural log of the absolute value of the secant 3t plus the tangent of 3t. So my final solution, y of t, is going to be my homogeneous part, or the complementary part, c sub 1, the cosine of 3t, plus c sub 2, the sine of 3t, minus the cosine of 3t divided by 3, the natural log of the absolute value of the secant of 3t, plus the tangent of 3t. If you want to know how I got to this point, I would recommend you give yourself a go on this integration. And if you are getting stuck, then I would recommend that you look in your calculus book under trig integrations. And that's what we end up getting after everything is completely factored and satisfied. And if you're wondering why I have the negative cosine 3t and the sine of 3t, before I even started, I just want to direct you to, going back up here, this right here, v sub 1 t x sub 1, v sub 2 t x sub 2. That's why I have the cosine. It's a negative because, as you know from doing the variation of parameters, here's what my v sub 1 was, which was a negative, and my v sub 2. So just in case I lost you somewhere, I just wanted to point out where this cosine 3t and the negative came from and the sine of 3t came from in front of this integration. Okay, let's do this example. Now, before I even start this example, I'm going to get you the complementary or the homogeneous part. And of course, this would have been y of homogeneous of t would be equal to c sub 1 e raised to the t plus c sub 2 t e raised to the t. And that's because I end up with this ODE has a repeating solution. So then my y sub 1 choice of t would be e to the t, and my y sub 2 choice of t would be, of course, t e raised to the t. I'm going to do my Wronskian because I know that's going to be required. E to the t, its derivative is e to the t, which we like. T e to the t, using the product rule, I'm going to get e to the t plus t e to the t. And I end up getting, when I get done, doing the multiplication and clearing up algebraically, I get e to the 2t. So then my particular solution, y of p, is going to be equal to my y sub 1, which is e to the t. And it'll be a negative times its integration of t e to the t, e of t, divided by e of the 2t multiplied by t squared plus 1 dt plus te raised to the t, the integration of e to the t, e to the t, e to the 2t, t squared plus 1 dt. And just as a reminder, the reason this is here is because this is my f of t. Okay, let's do my usual integrations. This is going to be equal to negative 1/2 e to the t, the natural log of 1 plus t squared. And you're thinking, why don't I have to do the absolute value? It's because 1 is positive and t squared will make it positive, so I don't need the absolute value symbols. Plus te raised to the t, the tangent inverse of t. Therefore, my general solution, y of t, is going to be equal to c sub 1 e to the t plus c sub 2 e to the t, it should be t, it should be, excuse me, it should be t e to the t minus 1/2 e to the t, the natural log of 1 plus t squared, plus t e to the t, the tangent inverse of t. Looking at this next example, they give us our y sub 1 and y sub 2. And that's because this is going to be ugly to try to find the homogeneous or complementary solution. But even before we do that, the first thing I need to do is divide everything by t. And that's because I have this t right there. So I end up with y double prime of t minus t plus 1 over t, y prime of t plus y of t is just equal to t. Now, because they give us our y sub 1 and y sub 2, we can go right to the Wronskian. So our Wronskian is going to be e to the t, its derivative is e to the t plus 1, its derivative is 1. Now, when we end up doing the Wronskian and cleaning up algebraically, I get negative t e raised to the t. So my particular solution, y, a particular of t, is going to be equal to negative e to the t. The integration of t plus 1 divided by t multiplied by t divided by negative t e raised to the t dt plus t plus 1 multiplied by e to the t times t and minus t e to the t dt. All right, when I get done, I'm going to get negative t squared minus 2t minus 2. So then my general solution, y of t, is going to be equal to c sub 1 e to the t plus c sub 2 e to the, c sub 2, this is just a polynomial part, t plus 1, minus t squared minus 2t minus 2. Now I can simplify this down by combining up my polynomial pieces. And so I'm going to end up with c sub 1 e to the t plus c sub 2 minus 2 t plus 1 minus t squared. However, c sub 2, which is a constant minus a constant, is still a constant. So this is still a constant. We're going to call it c sub 2. So we're going to just rewrite this c sub 1 e to the t plus c sub 2 t plus 1 minus t squared. And that is my final answer, and that is my final example. And that's it for this video.